To get started with creating our own custom schematics, let's create a blank schematics project using the Angular DevKit Schematics CLI. We're going to be using npx here, but note that alternatively, you could install the Angular DevKit Schematics CLI package globally and refer to it as schematics instead of using npx if you prefer. As for the name of our project, we chose schematics, but if you want to use something else, that's totally fine. Just make sure to put the outputted project in the schematics or tools directory so it doesn't get mixed up with your actual codebase. Great. The blank schematic we used creates either a new project or adds a blank schematic to an existing project. It can actually be used for both. Before we proceed, let's open up our tsconfig build.json file and add the schematics folder to the exclude configuration property just to make sure it doesn't get built alongside our application's code. With our boilerplate generated, let's navigate to this newly created schematics folder, and before we continue, let's install the schematics/angular package, as we'll need it later on in this lesson. Once the installation is complete, inside the source directory, we can see a new collection.json file. The collection.json file is the main definition file for the entire schematics library and contains definitions of all the schematics available in that library. So as we create more schematics, this file will have all of them listed out. We can see that our project currently contains one schematic with the name schematics, which might be quite confusing. Let's rename it to configurable-module. Also, as we can see, it points to the ./schematics/index file, and more specifically to the #schematics function within that file. Let's change the directory name to be configurable-module, and let's change the name of the function to be generate as well, as it makes a little more sense in the context of what we will be building here. And lastly, within this file, let's make sure we also update the description to be generates a configurable module. Excellent. Next, let's open up the index file located in the source/schematics folder and update the name of the function to be generate, as that's what we changed it to in our schema file. So far, we can see that this is a simple factory that takes an options argument and returns a rule, which takes in a tree and returns it back unchanged. The options argument here is an object that can be seen as the input of the factory, and based on those properties lets us determine the behavior of that factory. In schematics, the virtual file system is represented as a tree. A tree data structure contains a base, or a set of files that already exists, as well as a staging area, which is a list of changes to be applied to that base. When making modifications, we don't actually change the base itself, but add those modifications to the staging area. A rule object defines a function that takes a tree, applies transformations, more on transformations in a moment, and then returns a new tree. The main file for a schematic, which is that index.ts file, defines a set of rules that implement the schematic's logic. The transformation is represented by an action, of which there are 4 action types: create, rename, overwrite, and delete. Each schematic runs in a context represented by a schematic context object. Alright, so now that we understand the major building blocks of schematics, let's learn how things work by calling an external schematic, the Nest.js module schematic, and see what happens. In the code shown here, we are using the external schematic function to refer to an outside schematic and composing its rules onto our custom schematic. We also pass the options object in, but for now, we're temporarily hard-coding the name of the module to be placeholder instead of it being passed in via user input. Also, make sure to notice the chain function call we're using here, which lets us combine multiple rules if we need that ability. Currently, we only have one rule, so calling chain is not required, but eventually, we're going to add other custom operations applied here, so we'll add those later on. Lastly, let's prefix the tree parameter name with underscore just to instruct TypeScript that this argument is intentionally unused for the time being. Otherwise, the TypeScript compiler would throw an error at us when building the schematic. Great, so now let's save our changes, and before we test everything out, let's rename the inner schematics folder name to be configurable-module to reflect our configuration file. Now let's open up our terminals, and in a separate terminal window, navigate to the schematics directory with cd schematics. And then let's run npm run build ---- watch to build our schematics in watch mode. Once it's complete, let's switch to the original terminal window and execute the schematic with the following command that you can find below the course video as always. Remember that instead of using npx, we could have installed the Angular DevKit schematic CLI globally or locally within our project. Alright, so as we can see in our console, our schematic executed in debug mode. Debug mode results in the same behavior as if we ran a Nest schematic with the dry run flag, meaning that no changes get committed to the file system. Instead, we are shown the create, update, delete statuses of files that will be affected with our schematic. To turn debug mode off, we could just pass the --debug equals false flag, but since our schematic is not ready yet, let's wait to try this later on. Otherwise, things look just as we could have expected. A new module, named placeholder, would have been generated and the app module files would be updated as well. The external Nest module schematic is doing everything we could have expected it to do. Great! So we already know how to execute external schematics, but now, how can we accept parameters to control our schematic? Well, first, let's navigate to the collection.json file and add a new property to our schematic called schema, and make it equal to configurable-module/schema.json. Next, let's create that schema file in the configurable-module directory. Inside this file, let's paste the following schema. Like always, you can find the code here below the course video. Alright, so let's break things down here step by step. The $schema key points to the JSON schema defining this format. It is used by IDEs to do auto-completion, tools for validation, and it is entirely optional. ID is a unique ID for the schema in the collection. Type is a descriptor for the type provided by the properties, object in our case. But let's focus on the most important part here, the properties object. This object defines the available options for our schematic. Each option associates a key with a type, description, and optional alias. The $default parameter tells us that it will assume that the first argument given to this command is the value for the name property. The type defines the shape of the value we expect, and the description is displayed when the user requests usage help for a schematic. You can check out the Angular documentation for additional customizations for schematic options, linked below the video. Here, we specified that the required property is name, which determines the name of the module to be generated. We'll pass this option down to the underlying external Nest.js module schematic to show everything working here full circle. Note that you could of course add as many other properties as you need here when creating schematics. We're just keeping things simple for learning purposes. Let's save our changes, open up our terminals, and run the schematic again. So as we can see, the schematic CLI now prompts us for the name that we want for the module it will create. However, since we haven't updated the actual schematic, we can see that it still tries to generate the placeholder module instead of a module with the name we specified. To fix this, let's open up the index.ts file again and start by declaring a new configurable module schematic options interface. Next, let's update the generate function signature to, instead of using the type any for options, to use our newly created interface. And lastly, instead of passing the hard-coded placeholder string, let's pass down the options.name value. Let's save our changes again, open up our terminals, and run that schematic one more time, entering the name of recipes. And voila, as we can see, it generated the recipes module now. Perfect. All right, for the next step, let's update our generator to also generate the module definition alongside the module.ts file that gets created. To achieve this, inside of our configurable-module schematic folder, let's create another directory and call it files. We have to use the files folder name because it will be excluded from the TypeScript compilation by default. Check the tsconfig.json in the root of the project for more. This folder has to be excluded because we do not want to compile these template files. You'll see why in just a moment. Let's add one more nested folder inside of the files folder with the name __ name at __. The double underscores is a delimiter which separates the name variable from the rest of the normal string. Dasherize here is a helper function which will receive the value of the name variable and convert it to a kebab case string. And lastly, the @ symbol here is a way of applying variables to helper functions. So in our case, we're passing name into Dasherize. Inside that folder, let's create a file named __ name at Dasherize __ tree.module-definition.ts and paste the following code inside. As we can see, the code here is our regular template for configurable modules we covered in a previous lesson. Our goal is to auto-generate that file alongside the module file. Now, onto our schematic function. Let's add the following code to make sure it includes this new folder and file. And let's break everything down here line by line again. ./files is the location of the files we want to include. Options is the options passed into our schematic. And strings is a collection of utility functions, such as dasherize, which we used just a moment ago, provided by the devkit schematics. The template method generates our template based on those options and string utilities passed down to it. Next up, we're going to call the move method to move those files to a desired location, which in our case is the source folder. Once we have the template source, we can add it to the chain using the merge with function. Merge with merges an input tree with the source passed in. Remember, all this is happening within the tree's staged environment, so try to keep that in mind and think of what has happened there already and what your desired outcome is whenever you're building schematics. Let's save our changes, open up our terminals, and run our schematic again. And voila! As we can see, we have a new module-name.module-definition file auto-generated. Great! The last step we need is to configure our schematic to automatically import that definition into our module class and also make this class extend the configurable module class. This part is going to be the most tricky one yet, as we'll have to operate on the TypeScript AST or abstract syntax tree directly. Luckily, we can leverage some of the existing AST utilities provided by the Angular schematics, which should help make things somewhat easier. Note that we will be using quite a bit of advanced schematic utilities and methods and tools here from now on. So it's difficult to explain every aspect, but hopefully, once it's all pieced together, you'll have a good understanding of what's what and how things are all tied together here. So let's start by adding a new function called updateModuleFile that takes two parameters, tree and the options object, and then let's return the modified tree object back. Inside this function, let's start by defining two constants, name, which is a dasherized name, and module file path, which is the path to the module file. Next, using the tree object, let's retrieve the module file content with the readText method. Using module file path and module file content, let's construct a new TypeScript source file. Let's also make sure we import the TypeScript compiler API itself using import star as TS, just to make sure we're using the same version of TypeScript the schematic utilities support. Back to our function, with all of that in place, we can begin updating our tree. First, let's call the tree.beginUpdate method, passing in module file path as an argument. Next up, we'll use the insert_import utility function exported from the schematics/angular/utility/ast-utils package, passing in 4 arguments. TypeScript source file, our module file path, the item to import, which is configurable module class in our case, and the path to the file we want to import that item from. As insert_import returns a generic change object, we have to check if it's an instance of import change. And if so, using the update recorder and its insert_write method, we can insert a new line at the insert_import_change.pos position with the insert_import_change.toAdd content. Note that toAdd is just a simple generated string that we want to insert in our case. Lastly, after the if condition, let's commit the update using the commitUpdate method of the tree object, passing in update recorder as an argument. Just to test everything out, let's also add a console log here. And before we finish, let's make sure we actually use this function. So scroll down to generate and add update module file to the chain. Great. Make sure we save our changes, open up our terminals, and run the schematic again. And voila, as we can see in the console, our new import was added successfully. Fantastic. Last but not least, we have to make sure that our module class actually extends the configurable module class we just imported. So for this, let's first retrieve the class declaration node using the findNodes utility function from Angular's utilities. Here, we're passing the TypeScript source file as the first argument and the syntax kind, or the type of a node that we're looking for, as the second one. Also, as this function returns an array of nodes, and in our case we're 100% sure there's exactly one class in that file, we can simply retrieve the first element with array 0. But make sure to handle things accordingly here when building your own schematics in the future. Now to update our file, let's use the update recorder.insertWrite again, and for the first argument, we need to pass in the position, indicating where we need to put that new string. Since we know that our class is empty, meaning it doesn't have any methods, we can just take the end property of the class node -2 to get the desired position, so right before the brackets. Note that this might not always be the case for whatever you might be building in future schematics, so just keep in mind you might need a little different logic here if this was implemented on, let's say, existing modules that a user might already have in their codebase. For the second argument, let's pass the string we want to insert there, which is extends configurable module class. And that's it. Let's remove the console log, save our changes, open up our terminals again, and run the schematic. This time, let's pass in --debug equals false to actually apply the schematic to our project. And voila! If we look, we can see we have our recipes folder created with both the module definition file and our recipes module extending our generated configurable module class. Fantastic! Although things might have gotten a bit overwhelming near the end of this lesson as we started to really deep dive into some advanced schematic use cases and utilities, hopefully you can see the power and abilities you can have when working on schematics for your own organization. Whether it's generating libraries, microservices, etc., with batteries included, filled with all of the important but boilerplate code that your organization needs, or maybe you need a schematic to handle something else important, the sky's the limit. For more inspiration, check out how the Nest CLI schematics are built themselves to get some ideas on how to handle other tricky scenarios.